Okay. Okay, sorry about that. Okay, thanks for the invitation to speak, and it's good to be here. So in this presentation, I'll talk about dispersive shockwave propagation in two contexts, nonlinear optics and shallow water waves. These dispersive shockwaves are resonant due to the non-convexity of dispersion relation. This is all a joint work with Noel Smythe, Dimitri Frantzikakis, Theodoros Arikis, and Tim Marchant. And in the first part of the talk, I would like to talk about light wave propagation and defocusing nematic liquid crystals. And most of the asymptotic methods that I will discuss here are based on Whitham modulation theory. In the second part of the talk, I'll discuss a particular non-classical dispersive shockwave regime that we call cross-over dispersive shockwave, governed by the Kawahara and extended KdV equations when you use the shallow water wave coefficients. So I'll show you how we can do that using Whitham shock. And then at the end of the talk, I'll show you some future directions, which are basically Whitham shock applications. So the main focus of this talk is Whitham shocks. Okay, so I'll just highlight the main results, and for further details, you can refer to the papers. So starting with nonlinear optics, this is a nematic liquid crystal cell trapped between two plates of glass. There is a voltage source that generates a static electric field that rotates the molecules by an angle theta naught and to overcome Frederick's threshold. Frederick's threshold is the minimum amount of electric field required to rotate the molecules by a milliwatt laser beam. And then you have a linearly polarized electromagnetic wave going through the cell. And the main objective of this experiment is to see how a light wave interacts with nematic liquid crystal, which is useful when it comes to designing optical devices. Okay, so here are some snapshots from experiments that belongs to Gautana Asanto. This is when the light wave, it's cut. Sorry, it's cut. Anyway, when the light wave intensity is small, the light wave diffracts over the cell. And when you increase the light wave intensity, the nonlinearity kicks in, but due to the nature of nematic liquid crystal, the nonlinearity will be balanced with the self-diffraction effect. So what you have here is a bright self-confined region that we call bright solid wave. At the same time, you could have dark solid wave when you add the chemical compound azodite to your nematic liquid crystal. So in this case, you have self-confined region with low light intensity that we call dark solid wave. Okay, and the mathematical model that governs the complex envelope of the electric field is given by Annalisa equation, coupled with Helmholtz-like equation governing the molecular rotation. The positive sign refers to the self-focusing effect. The negative sign refers to the self-defocusing effect. Of interest here is the non-local parameter nu. By non-locality, I mean here is that the molecular rotation extends beyond the light wave intensity. And it's inverse proportional to the beam power. So when the beam power is low, you have high non-locality. An experiment is found to be typically of order 200. And if the beam power is high, you have low non-locality. In this case, the nematic equations reduces to the classical nonlinear Schrodinger equations. Okay, so we'll not be discussing solid wave solutions. We'll be focusing on shockwave solutions. So you need to consider the Riemann problem of your equations. So you consider rapid variation in the light wave intensity and consequently rapid variation in the molecular rotation because these two variables are connected. And then this is non-integrable system. You cannot solve it exactly. You need to implement numerical methods. So what you can do is that you discretize the space using fast Fourier transform, discretize the time-like dimension, the z, which is the length of the cell, using Runge-Kata method. And then, so what I'm doing here, I'm fixing the initial level behind, u negative equals 1, and I'm varying the initial level ahead, u plus. And then what I find that is that the solution is quite sensitive to the magnitude of the initial jump. Starting with a small initial jump, the non-dispersive region is given by a simple wave solution, the dispersive region given by a KdV-like dispersive shockwave, with a small resonant radiation propagating ahead of the dispersive shockwave, separated from it. If you increase the initial jump, that resonant radiation that was separated from the dispersive shockwave starts to interact with the dispersive shockwave, acting as a damping force on the dispersive shockwave, leading to modulational instability. You can see this better in the next regime that we call crossover dispersive shockwave. Now the resonant radiation is a wave of bigger amplitude, and it's a multi-phase wave train. The dispersive shockwave now is completely unstable. Whitham modulation equations here are elliptic. And in the long term, there will be more large number of randomly distributed solid waves. So you can think of this as a Salton gas, but in a non-integrable sense. And if you increase the initial jump, the resonant radiation becomes almost uniform due to the mean level change induced by the partial dispersive shockwave, taking the solution down to the initial level ahead. The dispersive shockwave now is completely gone and is replaced by a partial oscillatory Saleh wave that we call Whitham shock. But I will show you at the end of the talk that a Whitham shock doesn't have to be necessarily in this form. This is also a Whitham shock. This is also a Whitham shock. Okay. The next regime is the vacuum dispersive shockwave. The Whitham shock is still there. The resonant radiation is unstable, but it's taken down by almost uniform resonant radiation oscillating on varying mean level. The largest jump is when U plus equals to 0, so there is no dispersion. It's just non-dispersive solution. So it's similar to the dam break problem for shallow water waves. Okay, so to identify the dispersive and non-dispersive solutions, you use Madelung transformation. So you take the Madelung transformation, you substitute it into the nematic equations, and the nematic equations reduces to this dispersive hydrodynamic system. And when you check out the dispersive terms, you will end up with a non-dispersive system that you can solve using the method of characteristics. You take the non-dispersive system, you set it in Riemann invariant form, and then what you find out is the simple wave solution is given by the positive Riemann invariant and the C negative characteristics. And this solves the simple wave solutions in the numerical solutions. Okay. For the next part, the dispersive part, so I start with the perturbed dispersive shockwave and radiating dispersive shockwave. Now, because this looks like a KdV dispersive shockwave, what you can do is that you exploit multiple scale perturbation theory to reduce the nematic equations to the KdV equation. But here you need to go to beyond the classical KdV equation and incorporate the fifth order derivative because this is non-convex dispersive hydrodynamic system. And the fifth order term captures the effect of the resonant radiation. So it's essential to have the fifth order derivative. The next thing that you do is that you apply Whitham modulation theory, but you cannot do that exactly because this is non-integrable equation. It lacks exact periodic wave solution. So what you can do is that you map the fifth order KdV equation to the classical KdV equation for which you know the dispersive shockwave solution from Pettivitsky's work. And then what you say is that the nematic perturbed dispersive shockwave and radiating dispersive shockwave are nothing more than a perturbed classical KdV dispersive shockwave solution. Okay, for the crossover dispersive shockwave, so everything here is unstable, just do approximation. Okay, so the resonant radiation on average, you approximate it by a linear high frequency wave. Okay, so WKB approximation, which is actually derived by Gennady. And the dispersive shock wave is again unstable, so what you can do is that you treat it on average as a train of equal amplitude of solid waves. So what you do then is that you derive two conservation laws, mass and energy conservation laws, and then you integrate over the crossover dispersive shock wave structure from minus infinity to infinity. So the WKB approximation with the dispersive shock wave equal amplitude approximation determines the structure of the crossover dispersive shock wave. Okay, for the traveling dispersive shock wave, the WKB approximation ceases to work because now the resonant radiation is a wave of bigger amplitude, so you need to incorporate the nonlinearity effect. So what you can do is that you approximate this by a slowly varying Stokes wave and then use what we call Whitham modulation jump conditions, which is speculated by Whitham in his book and then pioneered by the work of Pat and Mark. So the way how you do this is that you start with the Lagrangian and then you derive conservation laws using Noether's theorem. So translation in phase gives mass conservation law. Translation in space gives momentum conservation law. Translation in time gives energy conservation law. And then you take the slowly varying Stokes wave solution, you substitute it into the conservation laws. You average over the fast scale, which is the phase, and then you end up with a system of PDEs in terms of the slowly varying wave parameters, which are the modulation equations. And you always close your modulation system with the conservation of waves. And then what you do is that you take these with the modulation equations, you set them as jump conditions. So you can think of this as the dispersive analog of Rankine-Huguenot jump conditions for classical shock waves that we call Whitham jumps. And this determines the structure of the traveling dispersive shock wave. Okay, For the traveling dispersive shock wave, the Whitham modulation jump condition ceases to work, but what you can do is that you observe that the resonant radiation is small, amplitude of the resonant radiation is small, so you can ignore it from the Whitham jumps, and in this case, the full Whitham modulation jumps reduces to the ones for compressible gas dynamics or shallow water waves. So approximately, you can treat this as a gas dynamic shock. Okay, so here are some comparisons. This is for the height of the leading edge of the dispersive shock wave. This is the velocity of the leading solitary wave edge of the dispersive shock wave. And this is the velocity of the trailing edge of the dispersive shock wave. This is the height of the resonant radiation. And the only comment that I would like to make here is on the discontinuity of the data that you see here. And this is due to the drastic change in the form of the dispersive shock wave as it moves from one regime to another regime. Okay, this is for the resonant wave number. This is for the background of the resonant radiation. This is for the shelf separating the dispersive shock wave and the simple wave solution. This is the Whitham shock velocity. And the only comment that I would like to make here is on the disagreement that you see in the resonant wave number and the crossover dispersive shock wave and vacant dispersive shock wave. And this is due to the fact that this is a the resonant radiation in these two regimes is unstable. So there exists no single dominant value of wave number. But we could be wrong about this, and the right way to do this is through Whitham shock. So I'll show you this in the end. Okay, so the next thing to do is to consider the transition from non-local to local. So what I'm doing here is I'm fixing the initial level, or the initial jump, and I vary nu. And as I vary nu, I come across all of the dispersive hydrodynamic regimes. At nu equals 200, I get a perturbed dispersive shock wave. At nu equals 40, I get a radiating dispersive shock wave. At nu equals 10, I get a crossover dispersive shock wave. At nu equals 3, I get a traveling dispersive shock wave. Nu equals 1, I get resonant analysis dispersive shock wave. Nu equals 0.5, I get just analysis dispersive shock wave. And the main goal here is not only to determine the dispersive shock wave solution when U plus varies, when the initial jump varies, but also when the nu varies. And also to determine existence borderline for each dispersive shock wave regime. But for this, you need to go beyond the fifth order KdV equation. You need to go to your multiple scale perturbation procedure, and you catch up the next order approximations. So you need to use the extended KdV equations by deriving 3 extra nonlinear dispersive terms. Okay, so I'll just, oops, why it looks like this? Okay, it looks different in my Mac. Okay. I think this is because this is Windows and this is Mac, so all of the plots are messed up. Okay, so red cubes are numerics, extended KdV predictions are red solid line, and Kawahara predictions are green dashed line. And as you see that the Kawahara equation doesn't predict the dispersive shock wave motion as nu varies. So you need the extended KdV equation, and I apologize for the plots. It look different in my Mac. Okay, so speaking of the crossover dispersive shock wave, I'd like to go to the next part, which is a new work with Noel Smythe. Whitham shocks are resonant dispersive shock waves governed by higher order KdV equation, which is still under revision. And what we would like to do is we consider reductive asymptotic models coming from the full dispersive Euler shallow water wave equations when you do not ignore the bond number there. So in the weakly nonlinear limit and long wave, you have the extended KdV equation, which I have just shown you earlier in the slides. But now with the shallow water wave coefficients, epsilon is the ratio between the amplitude of the wave and the depth. C1 is -3/2, C2 equals 23/4. C3 equals 5/2, C4 equals 19/40. And the special case of interest, which is well studied by Pat and Mark, which is the Kawahara equation, with the C1 and C2, C3 are all equals to 0. Okay, so consider again the Riemann problem. You come across similar hydrodynamic regimes. You have the radiating dispersive shock wave, which you can solve using higher order modulation theory or Gnad's method, whatever you like. The traveling dispersive shock wave, which you can use Whitham jumps to solve, which is also done by Pat and Mark. And the partial dispersive shockwave that you can use weakly nonlinear modulation theory to solve, done by Pat and Mark and Noel Smythe, but with this missing so far. Now, if you try to mimic what we did for the nematic crossover dispersive shockwave by treating this as a WKB approximation and this as a train of equal amplitude of solitary waves, that won't work. Even if you approximate this by a slowly varying Stokes wave, there is already an amplitude expression in the work of Pat and Mark. You take that and then you combine it with the train of solitary waves, that won't work. So you need to do that from a new point of view. And the right way to do that is through Whitham shock. You need to connect the resonant radiation ahead with the train of equal amplitude of solitary waves ahead by a Whitham shock. So basically, you generalize the work of Pat and Mark. So for the traveling dispersive shock wave, they had ahead weakly nonlinear Stokes wave, behind initial level U negative. For the crossover dispersive shock wave, you generalize this ahead weakly nonlinear Stokes wave, behind train of solitary waves. And the new Whitham modulation jumps reduces to the ones that Pat and Mark used for the traveling dispersive shock waves, when the amplitude parameter, the solitary wave amplitude parameter goes to 0. Okay, so I'll skip lots of details and then I'll show you just the comparisons. So circles are numerics, red dashed line are theory. This is for the resonant amplitude. This is the leading solitary wave height of the dispersive shock wave. This is the resonant wave number, and this is the Whitham shock velocity. Now, as you see, although this is a multi-phase wave train, unlike the nematic crossover dispersive shock wave, the resonant wave number is in excellent agreement. So we could be wrong about what we did for the nematic crossover dispersive shock wave, and the right way to do it is through Whitham shock. Okay, so that's for the Kawahara. For the extended KdV equation, you have the initial jump, you have epsilon, you have C1, C2, C3, C4. So there are many ways you can create crossover dispersive shock wave. So I'm just picking one. When you fix C4, you fix epsilon equals 0.15, and you take C1 equals C2 equals C3. So this is the, again, this is for the resonant amplitude. This is for the solitary wave amplitude, edge of the dispersive shock wave. This is the resonant wave number, and this is the Whitham shock velocity. And which is interesting here is that the validity of the Whitham shock for the crossover dispersive shock wave extends to the radiating dispersive shock wave. Okay, so you can also use the Whitham shock to predict the least resonant wave amplitude propagating ahead of the dispersive shock wave and use the Shalawative coefficients, and also to count the number of the solitary waves. But I'll skip that, and for that you can refer to the papers. Two problems of interest is to revisit the nematic crossover dispersive shock wave to improve the WKB approximation through Whitham shock. And what's more interesting is to look at the Whitham equation when you add the surface tension effect into account. Pat and Mark have shown that the Whitham equation possesses non-classical dispersive shock wave solution and have solved the traveling dispersive shock wave by Whitham shock. So if there is a classical dispersive shock wave, if there is a traveling dispersive shock wave, there has to be in the middle crossover dispersive shock wave that you can solve using Whitham shock. Okay, so I guess that's all what I want to say. So thanks again for inviting me to give this talk, and it has been full privilege and honor. And I apologize for the plots. It looks different in my PC, in my Mac PC.
Thank you, Saleh. And we even have time for questions, so maybe a couple of quick questions. Anyone? Yes.
So you're approximating this modulated dispersive shock wave as a train of solitary waves, and to evaluate your jump conditions, you somehow need to compute those densities and fluxes. So how do you do that analytically?
So something similar to what we did for the nematic equation. So for the, you mean this region, right? Mm-hmm. So you use the higher order solitary wave solution for the extended KdV equation or the Kawahara equation. And yeah, you just substitute it to your modulation equations.
So do you have a formula for those solitary wave solutions?
Yeah, but I'm not showing. I'm showing it. I have it for the Kawahara, but not for the extended. Yeah, it's this one. But this is for the single one.
Oh, okay.
This is
Thank
for
you.
a single solid wave. So what you have to do is that you have to consider them a train. So there will be capital N multiplied to the solid wave.
Any more questions? All right, let's thank the speaker again.